This video will introduce you to the 737NG bleed air system. We will see its purpose, operational characteristic for a typical flight. We will also see where to attach test equipment and some common troubleshooting examples. Before we get started, remember this video is for training purpose only. It does not supersede or take the place of any written documents of your company, the Boeing company, or any regulatory agencies. For the most complete and up-to-date information, always see the Aircraft Maintenance Manual or AMM before beginning any maintenance procedure. Also, be sure to know and follow all safety precautions, and finally, keep in mind that all pressure and temperature values mentioned in this program will be nominal. For actual pressure and temperatures, see your AMM. The 737 bleed air system supplies engine compressor air for wing and engine inlet cowl de-icing to the air conditioning packs for air conditioning and cabin pressurization, and for nitrogen generation system operation. The system uses ninth stage air during its low power settings and fifth air during high power settings. Note that bleed air is extremely hot and must be cooled before being sent to the AC packs. The pre-cooler is an air-to-air heat exchanger that uses engine fan air to cool the bleed. Note that the system is controlled using a series of valves, temperature sensors and pressure sensors, the high stage valve or HSV, and the pressure regulating and shut-off valve or PRSOV work together to control bleed air pressure, and PRSOV and the pre-cooler control valve or PCCV work together to control bleed air temperature in the HSV and PRSOV. Control air enters the valve actuator and is opposed by downstream pressure. The control pressure tends to force the valve open, and the down pressure tends to force the valve closed. So the position of the valve is the result of the force balance between the control pressure and the downstream pressure. Note that for both of these valves, the normal or relaxed state of the valve is to be closed. The PCCV is different in that control pressure is used to close the valve, since the normal and relaxed state for the PCCV is open, reducing the control pressure to the PCCV allows the valve to open. As we have seen, the system uses either ninth stage air or fifth stage air during different phases of operation. The flow of ninth stage air is controlled by the high stage valve and high stage regulator or HSR. Together, the HSR and HSV control ninth stage air to supply ninth stage air for low engine operation, regulate the pressure of ninth stage air to 32 psi, shut off ninth stage air during high engine operation and prevent reverse flow into the ninth stage. Bleed air pressure is controlled by the pressure regulating and shut-off valve or PRSOV, and the PRSOV is controlled by the bleed air regulator. Together they regulate bleed air pressure to 42 psi, prevent overpressure in the system, and in concert with the 450 sensor prevent runaway over temperature. The pre-cooler control valve or PCCV regulates the amount of fan air to the pre-cooler to regulate bleed air temperature. Now that we have seen that the HSV, PRSOV and PCCV control air flow through the system, let us take a closer look at how each of these valves is controlled. When engine starts, the HSV is closed. As pressure reaches 10 psi, the HSV is fully open. Note that HSR regulates the HSV control pressure to 16 psi. When the downstream pressure is more than 32 psi, it overcomes the 16 psi control pressure, causing the HSV to move towards the closed position. This balance of force regulates the ninth stage pressure in the system to 32 psi. If the ninth stage supply pressure goes more than 110 psi, the overpressure function of the HSR cuts off pressure to the HSR to prevent damage. Note that during engine start, reverse flow can occur. When this happens, pressure from the downstream sense line causes the HSR to remove control pressure from the HSV, which in turn causes the HSV to close, preventing the reverse flow to the ninth stage. As engine speed increases, fifth stage pressure will increase. When the fifth stage pressure reaches 32 psi, it will overcome the check valve and flow into the duct. This will cause duct pressure to increase beyond the ninth stage regulated pressure of 32 psi, causing the HSV to close. The bleed air system is now operating using fifth stage air. Note that the check valve prevents reverse flow into the fifth stage when duct pressure is higher than fifth stage pressure. Now let us look at the operation of the PRSOV. Remember that the PRSOV and the bleed air regulator work together to control the bleed air system pressure. When the engine starts, the PRSOV is closed. As pressure reaches 10 psi, the PRSOV is fully open. Note the bleed air regulator regulates the air to the PRSOV to 24 psi. This is enough to overcome the downstream sense air to the PRSOV and keep the valve open. As engine speed increases even further, the PRSOV will regulate the duct pressure to 42 psi. If the HSV fails and allows extremely high pressure into the bleed air system, the overpressure switch in the bleed air regulator will cause the PRSOV to close. Note, the overpressure switch will also cause the bleed trip light in the flight deck to come on. Now that we have seen how the bleed air system controls pressure, let us see how it controls temperature. As we saw earlier, the pre-cooler is an air-to-air heat exchanger that uses engine fan air to cool the bleed air. The pre-cooler control valve or PCCV and the 390 sensor control fan air to the pre-cooler. When the engine starts, the PCCV is open. The pressure rises above 10 psi. The PCCV starts to close as engine speed increases. So does the bleed air temperature. When the bleed air temperature reaches 390 degree Fahrenheit, the 390 sensor begins to open, reducing control air pressure. This causes the PCCV to open. When the bleed air temperature reaches 440 degrees Fahrenheit, the sensor will fully open, causing the PCCV to be fully open. As conditions change, the sensor will change the amount of control air vented and the PCCV will open or close as needed. If the PCCV cannot provide enough cooling air, the system can use the PRSOV to control temperature. If temperature reaches 450 degrees Fahrenheit, the 450 sensor will open. This reduces the control layer to the PRSOV, causing it to move towards the closed position. This reduces the amount of bleed air flowing through the pre-cooler with less hot air flowing through the pre-cooler. The pre-cooler can reduce the temperature of that air more effectively. If temperatures continue to rise, the 450 sensor will open fully, causing the PRSOV to move further toward the closed position. This reduces the pressure further, protecting the air conditioning packs and being leading edge from extremely high temperatures. If the temperature reaches 490 degrees Fahrenheit, the 490 over temperature switch will close the PRSOV and bleed trip light will come on. In summary, the purpose of the 737NG bleed air system is to determine whether the system uses 9th stage air or 5th stage air to meet requirements, regulate engine bleed air pressure, regulate bleed air temperature, prevents reverse flow into the engine compressors, and prevent bleed air from getting hotter than 490 degrees Fahrenheit. Now let us see how the bleed air system operates during a typical flight. At ground idle, once the engine speed is low, the HSV is open and system is running on the 9th stage air. At these low pressures, the PRSOV is also wide open. The temperature is usually low enough that the PCCV is closed. At taxi, the high stage system continues to supply the bleed air. Depending on throttle setting, the pressure may rise above 32 psi. If this happens, the HSV will act to regulate the pressure to 32 psi again. Depending on the throttle setting, the bleed air temperature may rise above 390 degrees Fahrenheit. If this happens, the PCCV will open to keep the bleed air at 390 degrees or below. At takeoff and climb throttle settings, the engine speed is high. Fifth stage pressure will increase above 32 psi, so that fifth stage air flows through the check valve. The increased pressure will cause the HSV to close. Fifth air will be above 42 psi and the PRSOV will modulate to keep the duct pressure at 42 psi. If the temperature is above 390 degrees Fahrenheit, the PCCV will open to allow cooling air to the pre-cooler. Typically, at the beginning of cruise, system pressure will be such that check valve will open and system will be using fifth stage air. Depending on the altitude, the air may get greater than 42 psi, so that the PRSOV will be regulating the pressure. Also, the temperature may be 390 degrees Fahrenheit or more, so the PCCV will open to regulate temperature. During cruise, the pilots continually reduce throttle settings to maintain speed and altitude as the plane becomes lighter due to fuel burn. At some time, pressure may go below 42 psi. In this case, PRSOV will be completely open. The PCCV will move towards the closed position as the temperature continues to decrease. If the airplane is heavy with full load of passengers and cargo, the throttles will be set higher to maintain speed and altitude. In this case, it is likely that the fifth stage pressure will remain above 32 psi and HSV will remain closed. If the airplane is lighter, the throttle settings may be lowered, reducing the fifth stage air pressure enough so that HSV will open, and the system will again be using ninth stage air. Note that depending on altitude, the HSV may open at the beginning of cruise. In descent, when the throttles are brought back to the flight idle, the ninth stage pressure will be below 32 psi. So both the HSV and PRSOV will be completely open. The temperature will likely be below 390 degrees Fahrenheit. So the PCCV will be fully closed. The fault isolation manual, or FIM, has charts that compare normal duct pressure to N1 and altitude. By knowing the altitude, N1 and pressure when a fault occurs, you can reduce the scope of troubleshooting efforts. To learn how to use this chart, let us take a closer look at how they are built. At the bottom of the chart is the scale for engine speed. Moving to the right on the chart corresponds with advancing the engine throttle. On the left side of the chart is a scale for duct pressure. These are lines that plot bleed schedules or duct pressure. Readings you should expect to see at given engine speeds for given altitude. This chart shows the pressure readings you should expect to see at sea level and 5,000 feet. There are also callouts that show the mode of operation and system should be in for each segment of these lines. This chart shows the bleed schedules for higher altitudes. Here's an example of how to use the charts. To make things easier to see, let us concentrate on the bleed schedule for 37,000 feet. The pilot has reported a low duct pressure of 25 psi while flying at 37,000 feet with an engine speed of 91% and 1. If we plot this data on the chart, we can see that the duct pressure was lower than the scheduled. We can also see that the system should have been on the fifth stage controlled by the PRSOV, since the HSR and HSV are not in control. At this altitude and engine speed, they cannot be part of problem and you can't need to troubleshoot them. Low pressure in this example could be caused by a problem with the PRSOV or bar. So troubleshooting efforts should concentrate on these components. But remember, If the cooling system is not sufficiently cooling the bleed air, the 450 sensor will cause the PRSOV to reduce duct pressure to increase cooling. So you should also troubleshoot the cooling system, including the PCCV, the 390 sensor and the 450 sensor. Another thing to keep in mind when using these charts is the pressure tolerances. Remember that when the system is operating in the regulated high stage mode, the HSV is regulating the 9th stage air to 32 psi plus or minus 6 psi, and when operating in the regulated low stage mode, the PRSOV is regulating 5th stage air to 42 psi plus or minus 8 psi. Now let us see where to attach test equipment and some troubleshooting examples. Caution: make sure to turn off supply pressure before removing any pneumatic lines, hoses or fittings. In order to see things more clearly, we will be using an engine setting in a cradle in the factory rather than one hanging from a wing. Simple test equipment has been developed to aid in troubleshooting. The equipment consists of hoses, gauges, regulators and fittings. You will see also need a source of supply pressure. In our example, we will be using nitrogen. See your AMM for more information. You use nitrogen and test supply assembly consisting of hoses, pressure gauges and regulators to simulate engine supply pressure in the system, and control pressure gauges, hoses and fittings to monitor the control pressure. Note that in some cases you may also need to monitor the movement of the valves. For our first example, note that the bleed air regulator or bar and the PCCV share the same supply pressure. On the left hand side, this T fitting takes air from the low stage duct and send it to the bar and PCCV. To simulate the air supply to the bar and PCCV for testing, remove the supply line from the anti-icing duct to this T node. To save time in the video, all fittings have been loosened ahead of time. Then attach the assembly supply hose from the test. Supply assembly to the T. Monitor the control pressure coming out of the bar. Remove the control pressure line from the PRSOV and insert the PRSOV test assembly between that line and the PRSOV. Now open the regulator on the test supply assembly. It will be providing the specified supply pressure to the bar. Check the control pressure from the bar to the PRSOV by looking at the gauge on the PRSOV test assembly and observe the movement of the PRSOV as you apply pressure. If control pressure is low, there may be a leak or faulty part. To isolate the problem, begin with the PRSOV. Turn off the supply pressure. Then remove the gauge line from the PRSOV and cap it. Now reapply supply pressure. If the control pressure is normal, then the problem is the PRSOV. If the control pressure is still low, then there may be a leak in the 450 sensor or its sense lines. To isolate the 450 sensor, turn off the supply pressure. Then disconnect and cap its control pressure line up near the left side of the pre-cooler. If the control pressure is normal now, then there is a leak in the 450 sensor line or its sense line in the pylon. If the control pressure is still low, the bar is not operating correctly or there is a leak in the sense line. If no leak is found in the sense line, the bar is at fault. To troubleshoot the PCCB and the 390 sensor, you will need the PCCB test assembly from the kit. Turn off the supply pressure, then go to the right side of the engine. Find the test port on the control pressure line to the PCCB. Remove the cap from the test port and attach the hose from the PCCB. Test assembly. Then reapply supply pressure. If the pressure on the PCCB test gauge is low, this may indicate a leak or faulty part. To eliminate the 390 sensor as the source of the leak, disconnect its control pressure line up near the right side of the pre-cooler and cap it. If the control pressure is still low, the problem is with the PCCB or its control line. If the control pressure is now good, either the 390 sensor or one of its control sense lines. One of its control sense lines is leaking. With good control pressure, you can use the needle valve on the test assembly. To simulate the venting action of the 390 sensor while you observe the control pressure, also observe the PCCB to see if it opens per the aircraft maintenance manual. If the PCCB does not open to the AMM requirement, you must replace the PCCB. Note that for the sake of this test, if the PCCB opens to within 30 degrees to fully open, it is considered open. A good reference to use is the inside of the screw head on the valve housing. To troubleshoot the high stage regulator, you will need the high stage test assembly. Recall that the supply pressure is taken from the high stage duct. Remove the supply line from the high stage duct. Then, using this special fitting from the test kit, attach the supply line to the hose from the test supply assembly. Remove the control line from the HSB and attach one hose from the high stage. Test assembly to the control line and the other to the HSB. Note, this is similar to what you did for the PRSOV. Now, apply supply pressure to the HSR. Monitor control pressure from the HSR to the HSB. And observe the movement of the HSB as you apply pressure. The HSB should open. If the pressure to the HSB is low, you will need to isolate the HSR and HSB to find the problem. Remove the test pressure line from the HSB. Then install a test cap with a 32 thousandths of an inch hole in it on one end of the line. Note, this cap has a hole because the HSR needs a small amount of leakage in order to regulate the control pressure. The normal leakage in the HSB is usually enough for this. There are instructions in the AMM for making this cap. If the pressure is still low, the HSR is faulty or there is a leak in the control sense line, and if the pressure is now correct, the fault is in the HSB. This ends our program 737 Next Gen Bleed Air System Overview and Troubleshooting. With the information presented in this video, you should have a basic understanding of how 737NG bleed air system works. Since the log report will tell you when a problem occurred, knowing what the system should be doing during that particular phase of the flight will help isolate the fault and give you a better idea of what tests need to be run. You should know where and how to attach the test equipment, run some of the more common tests and interpret the results of those tests. Here are a few final thoughts. Keep in mind that this video is for training purposes only. Any pressures, temperature or other readings given are nominal and for the sake of illustration. For complete, accurate and up-to-date information, always see the aircraft maintenance manual before doing any maintenance data.